This lecture is for sections 3.4 and 3.5, covering limiting reactants, percent yield, and chemical analysis. And what we'll be doing is we'll be looking at the idea of what a limiting reactant is, or limiting reagent is often a way it's called, and also how to identify one in a reaction. And then we're going to go over how to calculate what's called the theoretical yield for a reaction, and from that, determine the percent yield for a reaction, which involves an actual real experiment, not just thinking about chemistry. And finally, we're going to talk about the use of chemical stoichiometry to do chemical analysis, to find out how much of one thing is in a sample. So we'll start with limiting reactants and talk about the idea. The whole idea of limiting reactants is most reactions have more than one reactant. And when that's true, you need to determine, if you want to know how much product you're going to make from a reaction, you need to determine which of the two reactants is going to control how much product you're going to make. So if you had this reaction here, P4 plus 6Cl2 is going to make 4 PCl3s, the amount of product you make, the amount of phosphorus trichloride you make, is going to depend on either how much P4 you have or on how much Cl2 you have, and it's going to depend on both how much is present, both in mass and in moles, and also the relative numbers you need. So you need 6 Cl2s for every 1 P4 molecule. And that's what we're going to be looking at. We're going to be looking at how do you determine which of those two controls how much product you make. And the amount of product you make is going to be the theoretical yield. Okay, so let's look at a first example. And that is, if you have 200 tires and 75 steering wheels, how many cars can you make? Well, if you think about it, if you have 200 tires and 75 steering wheels, you can't make all the cars you would need if you had 75 steering wheels making cars, because the reaction overall is 4 tires. If you think about it as like a chemical reaction, 4 tires plus 1 steering wheel go to make a car. And to determine which is the limiting reactant, which of these are you going to run out of first as you're making cars, there's 2 ways to do it. There's a mole ratio reaction method. Cross out that N in your notes, mole ratio method. And what you do is you take the number of something you have, the amount you have, and divide it by the relative number you need. And so what you do is you'll take 200 tires and divide by 4, because you need 4 tires for each car made. And you compare that with 75 steering wheels, divided by 1 needed, because you only need 1 of those. And whichever of those is smaller is the limiting reactant. And that means as the reaction happens, that particular reactant will run out first. And so what happens here, this comes out to 50. That comes out to 75. That's smaller. So tires are the limiting reactants. Tires are going to limit how much you can make. And then you go on and do your stoichiometry calculations from that. That's one method. The other method is the maximum product method. And that's actually kind of a little cheesy, but it works. And what you do basically is just do the stoichiometry calculation for both of them, and whichever one's smaller, that's the one that is. So if you do stoichiometry calculation for tires, you'll have 200 tires times 1 car for every 4 tires, and that means you can make 50 cars. Or you have 75 steering wheels times 1 car per steering wheel, which means you can make 75 cars. And in the maximum product method, what you do is the one that's going to work is going to be this one. It really should be called the minimum product method, because the one that is going to actually control the reaction is the one you're going to make less of. So the one that's going to happen will be this one. So the fact that the tires will allow making fewer cars means that's the one that will limit the reaction. So you now know the limiting reactant is tires, and you can make 50 cars. All right, so let's look at a chemistry example. This is the reaction that's used for making iron, the metal iron, out of iron ore. Iron ore is actually made of a number of different kinds of iron oxides. So I'm using iron 3 oxide here. So 2 iron 3 oxides react with carbon, and they go to make 4 irons and 3 CO2s. And the question we're going to ask is, if we have 100 grams of iron oxide and 50 grams of carbon, which is the limiting reactant? Let's do that first, and then on the next screen we're going to look at how much iron can be formed. So we turn to the limiting reactant first. So using the relative number of moles method, what we do is we take the moles of iron oxide and divide it by its stoichiometric coefficient, 2, that's here. And we take the moles of carbon and divide those by the its stoichiometric coefficient, which is 3. So first thing you do is convert grams to moles of each. So 100 grams of Fe2O3 times 1 mole over 159.7 grams. To cut to the chase, I just gave the molar masses there. You would calculate those or do it on the web, and that comes out to 0.626 moles of iron oxide, Fe2O3. And then if we take 50 grams of carbon, we'll take times 1 mole over 12.01 grams. That's the molar mass for carbon. That's 50 divided by 12.01. That comes out to 4.16 moles of carbon. Then what you do is you take each of those and you divide them by their stoichiometric coefficients. So we're going to take 0.626 moles of iron oxide divided by 2 versus 4.16 moles of carbon divided by its stoichiometric coefficient, which is 3. This comes out to 0.313. This comes out to something like around 1.3 or something like that. 4.16. So 4.16 divided by 3. It's 1.39. Because the carbon ratio is bigger than the iron oxide ratio, iron oxide is the limiting reactant. So Fe2O3 limits the reaction. And when we say limits the reaction, what we mean is it limits how much product you can make, how much iron you can make, and also how much CO2 you can make. So that's important. Iron oxide is the limiting reactant, and you have 0.626 moles of it. So now we're going to go ahead and figure out how much product we can make, and we're going to expand the way we've done this from before by using what's called an amounts table. An amounts table is also a moles table, a table of the amounts of moles of things. And the key here is what we're going to do is we're going to put in our initial amounts of our reactants and products, and then figure out what happens. So we start with, on the previous screen, we had 4.16 moles. I'm just going to not put in units here, but these are all moles. And we had 0.626 moles of iron oxide. 6 moles of iron oxide, 4.16 moles of carbon. And we started with 0 amounts of iron and of CO2. And the key here is all of the limiting reactant is used. That's the key. The limiting reactant gets used up. The other one is the reactant in excess. So carbon is in excess, is the way you say it. It's the reactant that is not used up. So the change for the iron will be minus 6.626, and you're going to end up with no iron oxide left over because it gets used up. That's the whole idea of it being the limiting reactant. And you can look at the products. So the amount of iron that's going to be formed is going to equal 0.626 moles of Fe2O3 times 4 irons for every 2 Fe2O3s. That's from the balanced equation. This 4 and this 2 come from our balanced equation, the 4 and the 2 there and there. And so that comes out to be 0.626 times 2. So the change that happens is it's 1.252 moles of iron, and therefore you start with 0 and you added 1.252, so you make 1.252 moles of iron when the reaction happens. The amount of CO2 you make is going to be 0.626 moles of iron oxide. You always use the amount of limiting reactant to define how much reaction happens for everything. And it's going to be 3 CO2s, that's from that 3 right there, over 2 iron oxides. So that's going to come out to a little bit around, it's going to come out around 1.626 times 1.5, 0.939. That's going, so 0.939. So what that means is because CO2s are a product, you're going to add 0.939 moles. You had 0 to start with, so you end up with 0.939 moles of CO2. The cool thing here is that you can also determine how much carbon reacted. The amount of carbon reacting, carbon lost, is going to equal 0.626 moles of iron oxide times 3 carbons for every 2 iron oxides. And that comes from looking at the stoichiometric ratio of iron oxides reacting to carbons reacting. So that's going to be the same number, because the ratio is the same number as CO2 we had, but in this case it's going to be a minus, because the carbon is reacting. It's a reactant, so it's going to be decreasing in amount. So you can now look at what the amount of carbon left over is. So it's 4.16 minus 0.939, and that comes out to 3.221 moles of carbon that are left over. So at the end of the reaction, you know you have 0 moles of iron oxide, 3.221 moles of carbon, 1.252 moles of iron, and 0.939 moles of carbon dioxide. And you can then convert those into grams. So I'm not going to show that out, but I'm going to take the 3.221 and multiply it by 12.01, because that's our molar mass for carbon. So you're left with 38.7 grams of carbon, 1.252 moles of iron times its molar mass, which is around 58, I think. I don't know offhand. Let's look it up. Can't see me, I'm grabbing a periodic table from a book on my shelf. Iron is 55.85. So I'm going to take 1.252 times 55.85. That comes out to 69.9 grams of iron that you can make. And the amount of carbon dioxide you make is 0.939 times 44.01. That's the molar mass for carbon dioxide, which is 41.3 grams of carbon dioxide that you can make, that you will make, or you can make. And that's it. So you know exactly how much of each entity, either reactant or product, that will be remaining when the reaction is complete. And so this whole idea of a moles table allows you to kind of keep control of both the reactants and keep track of both the reactants and the products. All right. Now let's talk about the percent yield. For percent yield, what you have is the idea is that when you do a reaction, you don't actually get all of the product. Normally, you don't get all the product that you might get from doing your stoichiometry calculation. So when you do this stoichiometry calculation, you get this, say you'll make 69.9 grams of iron. That's how much you could potentially make using the reactants you started with. So when you use the reactants you start with, it doesn't mean you will make that much. It just means that's the most you could possibly make. And you very rarely do. Almost all reactions go in less than 100% yield. The yield is how much you actually obtain. So when you go to lab and do an experiment, you make something and you isolate it, you weigh it at the end. The weight that you get at the end is the experimental yield. So the top number is always by experiment. You can't calculate that. It's just something you do in lab. The theoretical yield, the theoretical amount you could have got, that's just a stoichiometry calculation. So when you do your homework and it says, this many grams of that, this many grams of that, how many grams of product do you make, the result of that calculation is the theoretical yield. And then what you do is you divide those two and times by 100, and that gives you the percent yield. So let's look at an example of that, and let's do it using the alum lab that is frequently done. So let's say that you do this reaction, you react aluminum with first potassium hydroxide and then sulfuric acid, and eventually you make alum, which is that hydrated potassium aluminum sulfate. Let's say you start with 0.985 grams of aluminum, that's your reactant, and you end up making 14.8 grams of the alum. What's the percent yield? The key to this is that what you do is you have to calculate the theoretical yield first. The experimental yield is this. That's just given. That's the amount you got when you did the reaction. So you have to calculate the bottom number, and you're just given the top number. And by given, meaning you would do the experiment and just weigh it. The next key then is to determine the theoretical yield. And here's the idea. The one thing to realize is that for every mole of aluminum, you make a mole of alum. And you know that either by following through the reactions or just to realize all the aluminum atoms, all of the products end up making that alum. So all the aluminums are there. So what we're going to do is we're going to go from grams of aluminum to moles of aluminum. Moles of aluminum is going to equal moles of alum because they are made 1-to-1. And for moles of alum, we'll go to grams of alum. And that's going to equal our theoretical yield. All right, so let's start with molar masses are conveniently handed to us here. So 0.985 grams of aluminum times 1 mole over 26.98 grams. That equals 0.985 divided by 26.98. 0.03651 moles of aluminum, which means that you have 0.03651 moles of alum, which is KAlSO4 2.12H2Os. And then you take that and convert that to grams of alum. So 0.03651 moles of potassium aluminum sulfate .12H2O. The term for the term like a di or tri or whatever for 12 is dodeca, so dodecahydrate, times 474.37 grams over 1 mole. And that gives a theoretical yield of times 474.37, 17.3 grams. Let's pause for a moment and just reflect. Isn't that amazing that you can take 0.9, like less than 1 gram of aluminum, goes to make 17 grams, theoretically, of the alum. And that's because the product has such a larger molar mass than does the reactant. So finally, the percent yield is the amount you did get, 14.8 grams, over the theoretical amount, 17.3 grams, times 100. And you put the little percent on there just to put the percent on. So divide by 14.8 over x. Oops, just wrong. 14.8 divided by 17.3. That gives 85.5% yield, which is not bad. That's a good yield. All right, that's how that works. Finally, we're going to talk about chemical analysis, and the idea is to use stoichiometry to determine how much is in something, how much of one substance is in a sample. And so we're going to do a little example here where we have a soil samples analyzed, and we're looking for how much iodine is in it. And this is not a particularly realistic example. I just made it up. Let's say we have a 2.68 gram sample, and you treat it in a way that all the iodine dissolves and turns into iodide ion, I- ion. So all the I- ion ends up in solution. And then in solution, you do this reaction here. We'll see reactions written this way in the next chapter. So all of the iodide ion reacts with lead ion to make PbI2. When you do this, you end up with 0.339 grams of the lead iodide, PbI2. And what we want to know is what's the percent of iodide in our original sample. So let's write out what that is first. Percent iodide, or iodine, doesn't really matter, is equal to the grams of iodine over the grams of the sample times 100. So we need to find grams of iodine and grams of the sample. Grams of the sample is easy because it's given to us. It's 2.68 grams. So what we really need to do is find the grams of the iodine. And this a lot of analyses are done this way, where you kind of leach something out of a sample, then react it so you can isolate it in some other chemical compound, and then find out how much of it was there. So to find out how much iodine we have, well, you're going to use compound stoichiometry. So we're going to take 0.339 grams of PbI2, and we're going to convert that into moles of PbI2. Moles of PbI2. So it's going to be 1 mole of PbI2 divided by its molar mass, which I will cheat and do on my other computer here that you can't see. .461 grams per mole of that. So 0.339 divided by 461. Whoa. That has a large molar mass, by the way, because both lead and iodide both have large molar masses, and there's 3 atoms. So that gives me 7.35 times 10 to the minus 4 moles of PbI2. Then 7.35 times 10 to the minus 4 moles of PbI2. We're looking for iodine, and there are 2 iodines per mole of PbI2. So it's 2 moles of iodine per 1 mole of PbI2. So that means we're going to have times 2, 1.47 times 10 to the minus 3 moles of iodine. Twice as much iodine. And then we're going to convert that into grams of iodine. So it's 1.47 times 10 to the minus 3 moles of iodine times its molar mass, which is 126.9 grams of iodine per mole. That's just from the periodic table. Times 126.9. And that gives us a mass of 0.187 grams of iodine. And therefore, those 3 little dots there mean therefore, the percent of iodine is equal to 0.187 grams of iodine over our sample mass, 2.68 grams of sample, times 100. That comes out to 6.96%. Most soil samples will not have that much iodine. If you spilled a bunch of iodine on some soil, maybe then, but generally not. Okay, so the idea here is that this isn't the way it's always done. The idea, the important part is what you do is you're looking for how much of a sample, how much particular chemical entity is in a sample. You know the size of the sample, and you need to figure out some chemical way of determining how much of that one thing was in the sample. In this case, we know a way of leaching it out and getting it to be a solid we can measure, and then if we know how much of that solid, we can figure out how much of the iodide is that solid. Okay, now let's look at another example. Let's look at a CHO analyzer, and this is used exclusively for doing analysis of hydrocarbons or hydrocarbons that also contain oxygen. And the way it works is you have some compound here, and you burn it with oxygen, and you have some compound CXHYOZ, and you react it with oxygen, and you make water and CO2. And you can't balance the reaction because you don't know the formula. You're looking for the formula of this compound. What you do is you know how much sample you burned, and you can figure out how much water you got and how much CO2 you got. From that, what we're going to do is we're going to use the amount of water to find moles of water, and for moles of water, we're going to find moles of hydrogen. From the grams of CO2, we're going to find moles of carbon, and for moles of carbon, we're going to find, that's it. We're just going to find moles of carbon. We're going to find moles of CO2, sorry. Moles of CO2, and for moles of CO2, we'll find moles of carbon, but those are the same. And then we'll also find grams of hydrogen, and we're also going to find grams of carbon, and from those two together, oh my gosh, we'll find grams of oxygen, and from grams of oxygen, we'll find moles of oxygen. Oh, we're going to be here all night. All right, so the idea is we have amounts of water and CO2, and when we burn it and get those as samples, it'll tell us relative numbers of these two elements. And by mass difference, we'll find out how much oxygen was there. And eventually we'll get the moles of all three and be able to determine the empirical formula, which is what we're doing, finding the empirical formula of the stuff we're burning. All right, so let's start to it. 0.240 grams of water. We've done grams to moles enough. I'm just going to convert that to moles of water without writing it out. The screen is only so big. So that's 0.0133 moles of water, which means you have twice that moles of hydrogen because every water has 2 hydrogens. So that means you have 0.0266 moles of hydrogen. While we're here, I'm going to convert that to grams of hydrogen times 1.01. So that comes out to 0.0269 grams of hydrogen. We really want the moles for figuring out the empirical formula, but we're going to need the grams in a minute because we need to figure out how much oxygen we had, and you can't measure oxygen directly in this experiment. For the carbon, we have 0.882 grams of carbon dioxide. 882 divided by 44.01, which is the molar mass for carbon dioxide. So that's 0.0200 moles of CO2, which means you have that same number of moles of carbon, 0.0200 moles of carbon. And then we'll go ahead and convert that into grams of carbon, 12.01. So 0.241. I'll do 0.07 grams of carbon. Okay, so remember, when you figure out the formula for compound, you need to figure out the relative numbers of moles of the elements in that compound. We can do that already for carbon and hydrogen because we know how many moles of hydrogen and we know how many moles of carbon. The thing that's missing is the moles of oxygen. And the problem is, when you do your reaction, you end up with oxygen both in the water and in the CO2, and you add oxygen here. So there's no way directly from the reaction results that you can tell how much oxygen was there to begin with. You can figure out how much carbon, because all of the carbon here ends up in CO2. All the hydrogen ends up in water. So those you can link directly, but the oxygen you can't. The way you figure out the oxygen is by difference, because the compound is made of carbon, hydrogen, and oxygen, and you know how much carbon and you know how much hydrogen. So the grams of oxygen is going to equal our sample mass, 0.588 grams, minus the amount of hydrogen, 0.0269 grams, minus the amount of carbon, just 0.2407. And that gives us, what does that give us? 0.588 minus 0.0269 minus 0.2407, 0.3204 grams of oxygen. And let's go ahead and convert that into moles by dividing by 16. 0.0200 moles of oxygen. Whew! So now we know we're close, you can feel it. We have 0.0266 moles of hydrogen, 0.0200 moles of carbon, and 0.0200 moles of oxygen. So fortunately, the moles of oxygen and carbon are the same, so they'll have the same number in the formula. And so what we now do is we find the number of hydrogens over the number of either carbons or oxygens is going to equal 0.0266 over 0.0200, and that is equal to 0.0266 1.33, which is 1 1/3, which is equal to 4/3. And so the ratio of hydrogens to carbons is 4/3, which means you have 4 hydrogens for every 3 carbons. So our empirical formula is C3H4O3. And that's how it's done at Galbraith Labs for $25. That is the end of this lecturette.